Now that we know about solutions, let's talk about concentration. So this is the calculation part of the chapter where we actually learn about concentrations. So there are a number of ways that you can actually do the concentration calculations. You have to be a little bit careful when you read the question and try to solve a problem because there are a couple of things involved here, okay? So you can have a solute dissolved in a solvent to give a solution, right? That's what a solution is. So when you're calculating the concentration, you could be calculating the concentration of a solute in a solvent, or you could be calculating the concentration of a solute in a solution. Okay, those two are two different things because in a solvent, there is no solute. But in a solution, you have the solvent as well as the solute. So the quantities, the numbers will change, okay, in those cases. So I will make sure that you kind of get that idea when we start doing the calculations, but keep that in mind when you're reading all these concentration values. Okay, so here are a few that are given to you. The formulas for all of these are given on the next slide, so just be a little patient. Molarity is the one that you're very familiar with because we did that in Gen Chem 1. And molarity is moles over liters, and it's usually used for solutions, and it's very easy to do. And this is how you would find solution concentrations in almost all labs, okay, in chemistry. Then there's a mole fraction. Mole fraction, as it says, would be a fraction of mole to mole ratios. And this is used for gas and vapor pressures, okay? And so when we get to there, you will see how we actually use this. Molality is slightly different. Molality is moles over kilograms of solvent. And the interesting thing about this one is that it's temperature independent because you can change the solution and the solubility with temperature. So that's what molarity does. But in molality, you have absolute quantities, okay, in there. So when you need to know absolute quantities and by gram, then molality is a good solution concentration to have. Then you can have percent by mass and you can have percent also by volume, okay? So in these cases, the calculations are not all that accurate. They can be accurate, but you know, when you're dealing with just general dilute solutions, then you will make them as percent solutions. So this is some of the basic solution concentrations that you will find. And then you can also convert between any of these different units. Okay, the only thing is that you may actually need density in some cases, you may not need the density in some cases. If you're given volume and you're asked for mass calculations, then you will need density. Okay, so on. So it depends on what kind of calculation you're doing. But you can convert all of these from one to the other, and which is what we're going to do, okay, in this little presentation. So here are the different units that you will need. So please keep this handy, and eventually you will see that, you know, this becomes very easy. It's not hard to do it all. Molarity, as you already know, is moles of solute over liters of solution. Please keep this in mind. This is liters of solution, not liters of solvent. Okay, so this is solution. Mass percents are different kinds. Okay, mass percents can be mass by volume, volume by volume. Okay, and of course the denominator is going to be the solution, not solvent, solution. And the top quantity is the mass of or the volume of the solute. So this one is given only for the mass percent, but the rest of them are going to be similar, which means that if you have gram by volume, then you will have mass of the solute up here and volume of the solution down here. Okay, and so that's how you would do mass percent calculations. Molality is moles over solute and then kilograms of solvent. So you can see that molality is the only one that has to deal with solvent. All the other ones have to do with solution. So this is very unique in that case. We don't use molality so much in chemistry. Molality is used a lot more in biology, where they need to know the grams of substances that they need to use. For us, we usually work in molarity or mass percents. Okay, those are our two things that we usually use. But anyhow, we're going to do conversions for molality also. One thing I want you to keep in mind here is the units, okay, and how they are actually designated. For molarity, you can use moles per liter, but look at the symbol for it. Okay, this is capital M. And for molality, it is small m. Now with the small m over here, this is actually going to be in italics. And this is a little bit hard to write when you're writing in case of in your handwriting. Okay, this is going to be tough to write. So I would suggest you either put you underline it, or you write the units, which is moles over kilogram of solvent. Okay, do something so that you know that you're talking about molality and not meters, things like that. Okay, so please be clear in your writing, okay, for this one. Mole fraction is designated by X, and X is not just an X, and X is like a nice wavy X. And this is the moles of solute over the total moles of the solution. Okay, and so this one actually does not have any units, because when you're talking about a mole ratio or any kind of a ratio, then the units cross out. Okay, so moles and moles will cross out, so there are no units for this, just a ratio. And then there's a parts per million and parts per billion, okay, of any substance. Now the parts per million has to do with 10 to the power of 6, right? Because 6 zeros make up a million, and then 9 zeros make up a billion, okay, of anything. So the reason that you see these little stars on here is because this has to do with the units that you're using here. Okay, so for example, a mass of 1 microgram over 1 kilogram, that might lead you to have a billion, okay, of ppb. So again, ppm, ppb, these are going to be ratios. They're not units. Okay, so you have to put your own units there. So I can put any units so long the unit on the top is 1 and the unit at the bottom is a million. Okay, so that it's 1 in a million. Okay, whereas in this case the solute is going to be 1 in a billion. Okay, that's all. So my unit has to be that ratio. Okay, so it doesn't matter whether I'm using liquid or solid or whatever kind of a unit. Okay, so those are your formulas and units for these solutions. So let's look at the first example. Now the next few slides are actually all examples, so if you don't want to listen to this, that's fine. You can print this and study this on your own also. However, I'll go through with this step by step. So here's the first one. An experiment calls for 36 grams of a 5% aqueous solution of potassium bromide. Describe how you would make up such a solution. So 36 grams of 5% solution that you need. Okay, so how do we set this up? A 5% solution would have 5 grams of KBr, potassium bromide, in 100 grams of solution. That's what a 5% solution means, which means that the remainder of the 100 grams is water, which is that you have 95 grams of water and 5 grams of KBr, potassium bromide. So use this ratio, okay, to determine the amount of potassium bromide you would need in a 36 grams of solution. So here is the setup. Okay, you have 36 grams of solution that you need, and in that solution 5 grams has to be potassium bromide and 100 grams is the solution. This is the percent solution. Please make sure you write your units, because you can see the solution and solution, so you know how to cross that out. Okay, so and again, remember, always start with what you know, okay, and what you're given. So 36 grams of solution is what you're given. I would always start with that, and I would use my percent solutions or concentrations as a conversion factor. Okay, so this is a conversion factor of some sort. So if you're setting up a dimensional analysis, then this becomes easy to follow. Okay, so that means now I have 1.8 grams of potassium bromide. So I have 36 grams of solution, and in 36 grams of solution, 1.80 grams is potassium bromide, which means the remainder of the solution is water. So all you have to do now is subtract 36 minus 1.8, or subtract 1.8 from 36, and so 34.2 grams is water. So what do you do in the lab? Okay, in the lab you will go in and measure out 1.8 grams of potassium bromide and dissolve it in 34.2 grams of water to give a 5% solution. Simple enough. Okay, so next one then, this is on molality. Iodine dissolves in a variety of organic solvents. For example, in methylene chloride forms an orange solution. What is the molality of a solution of 5 grams of iodine and 30 grams of methylene chloride? So keeping it simple, molality is moles of solute over kilograms of solvent. So essentially what we have to do is convert the solute into moles and convert the solvent into kilograms. It's all about units, okay, in this case. So first things, we can write down our data, and writing down the data is an important thing, especially when it gets to more complex problems. This was pretty straightforward, but still, okay, if you want to, you should still do this. Then what we're going to do is exactly what we said. We'll calculate the moles of solute and convert the mass of solvent to kilograms. Again, just unit conversions going on here. So we can do everything at the same time, okay, which means that we can have 5 grams of iodine over the solvent. Now, this is technically speaking our formula also, which is a solute over the solvent, okay. And so what we have to do is make sure we convert them into the right units. So unit conversion going on. For the first one, we have 5 grams of iodine being converted into moles of iodine, and 1 mole of iodine has 253.8 grams of iodine. That's that conversion there. And in the next step, what we're doing is converting the grams of solvent to kilograms of solvent. It is important you keep your units in the right place. So remember, grams is at the bottom here, so kilograms should be at the bottom here for molality. Okay, so then you go ahead and cross out your units also. Because again, in any kind of dimension analysis, it's really nice to keep a track of your units. Okay, so if you do this, you probably will be fine. Okay, so make sure your units are in order. So here we have moles of kilograms left. Okay, and that's the final answer. Simple enough. Next question is about mole fraction. Okay, so again, we have a solution of iodine in methylene chloride. Yeah, it's a beautiful solution. And now in this case, we have 5 grams of iodine and 56 grams of dichloromethane or methylene chloride. In case of mole fraction, you would need moles, okay, of both. So we will start our calculation by starting with moles, and then we'll add the moles, and then we'll calculate the mole fraction. Okay, so keeping it straightforward, here we are. Calculating the moles of iodine, okay, very simple, and then calculating the moles of the solvent, which is 56 grams of dichloromethane. Use the periodic table, find out the moles. Then to calculate the mole fraction of iodine, this is the moles of iodine. So then you'll add up these 2 moles together to get the total moles, and then you'll calculate the mole fraction of iodine, and then you can also calculate the mole fraction of dichloromethane, okay, because that is what we're supposed to calculate here. So very simple, straightforward, okay, keep it that way, and that's it for this calculation. This example is a little bit of a unit conversion now. Previously, what we were doing is we were given the quantities of the solute and the solution, and we were supposed to do the calculations for the concentration. Now what we're doing is unit conversions, which means that we're going to convert one form of concentration to another form. Okay, so here is a question. A bottle of bourbon is labeled 94 proof. 94 proof is actually half of that number would be the percent, okay, of the solution in there. So 100 proof is actually 50%, okay, of an alcohol solution. So 94 proof, meaning that is 47% by volume of the alcohol in water. What is the mole fraction of ethyl alcohol in the bourbon? The density is given to us as 0.8 grams per mil. Now in this case, since we're going to mass to mole fraction, you need to know the mass of something, which is why the density is given to us. Because when you have a solution of alcohol in water, it means that you have a volume by volume percent. And just because you have a percent doesn't mean that it has to be volume. And just because you have liquids doesn't mean that it has to be volume. You can actually weigh liquids also. But usually it's easier to measure liquids in milliliters. Okay, and so anyhow, you have to be careful as to what data is given to you. So here is 47% by volume of alcohol in water, and then the density. Okay, so let's look at that. First of all, there was no volume given to us as to how much there is. Okay, so you can safely assume it's going to be 1 liter. If you don't want to assume 1 liter, you can also assume 100 milliliters because this is a percent solution. So in this case, if you assume it's 1 liter, then there is 470 milliliters of alcohol and 430 milliliters of water. Okay, now if you were to assume it's 100, then obviously you'll remove the zeros. Your calculations will still be the same because eventually we're going to go to mole fraction, and there are no units for mole fraction. So whether you start with 47 milliliters of alcohol or 53, it's going to turn out to be the same calculation. All right, so in any case, And then what we're going to have to do is calculate the mass of both. Why? We have to calculate the mass because we need to find the moles. Okay, you can't find moles from liquids, so you have to find the moles of the mass, which is grams, and then of course that's where you need the density. Okay, is to convert the milliliters into grams. Okay, and then we'll find the mole fraction. So let's get started. So first one, 470 milliliters of ethanol, and then there's the mass conversion right here. So they use the density to find the mass of ethanol. Once you know the mass of ethanol, then you convert it to moles by calculating the molar mass of ethanol. So C2H5OH, that's the formula. So you calculate the formula mass of that, which is 46.08. Okay, and so you end up getting 8.16 moles of ethanol. You would do the same thing for water. 530 milliliters of water, and then the density here is going to be 1 gram for water. Okay, remember, this is 530 milliliters of water, not 530 milliliters of solution. Okay, so ethyl alcohol is 0.8. But 530 milliliters is water. So you're trying to find out the mass of water here. So that's 1 gram per mil is the water. And then you convert it to moles, okay, which is 18.02 is the mass of formula mass of water. So you get 29.4 moles. Okay, and now what we have to do is the mole fraction of ethyl alcohol in bourbon. So in that case, we now need to add up both of these moles. We end up getting 37.6, and you find the mole fraction as we did last time, okay, with the mole fractions. So that is how you would go about to use the density of substances. So if you're given the density of anything, please make a note and see that, you know, whether you need it or not. Sometimes you may not need it, but, you know, most times you will. Otherwise, why would it be given to you? Here's another one for unit conversion, going from molality to molarity. Okay, so citric acid is often used as fruit beverages to add tartness. Okay, and so then an aqueous solution of citric acid is 2.331 molal, not molar, molal, citric acid. What is the molarity of the solution? The density of solution is given to you. Okay, and so let's get started. 2.331 molal means that you have 2.331 moles of citric acid in 1 kilogram of solvent. Okay, molarity, however, is given in solution. It's not given in solvent. Okay, so which means our strategy has to be that we convert the moles of citric acid to mass. We find the mass of the solution, and then we'll use the density to find the liters of solution, because that's where we need to go. We need to find the moles, the liters of solution over here. Okay, so that's going to be our strategy. So the mass of solute, first of all, the moles is given to us, so 2.331 moles, and then we calculate the formula mass of citric acid, which is 192. So that's what the mass of the solute is. The mass of the solvent is 1 kilogram. Okay, that's the mass of the solvent. So the mass of the solution then becomes 447.88 plus 1000 grams, okay, of solutions. This is now the mass of the solution. Once we have the mass of the solution, now we have to find the volume of the solution. So we're going to use the density of the solution to find the volume of the solution. That's why we needed to calculate the mass, okay, of this. Now, remember, eventually, when we get to molarity, molarity is still moles, okay, of solute. So which means that we will still need this number, except that we need this mass over here to find the mass of the solution, so we can find the liters of the solution. I think this will make sense. I hope it is. So the liters of solution then is 1.447 with the mass of the solution here, and convert it to milliliters using the density, and then finally convert it to liters. Okay, because remember, for molarity, it's moles per liter of solution. So then you have 1.267 liters. One little word of caution over here when you're trying to do all of these calculations, where one number goes on to the next number, to the next number, to the next number, is keep your, or I should say, do not round off too much. Okay, so don't round off over here. You can see from here that your data is 4 significant figures. Okay, But this is not your final answer with these moles, and neither is this mass. This is not your final answer. So I would suggest that you don't round off anything. Keep it up to 5 or 6 significant figures until you get to the final answer. If you start rounding off here to 4 significant figures, your answer is going to be different, okay, from what it should be. So please don't round off, okay, until you get to the end of the answer. So now I'll start rounding off at the end because I'm getting towards the end now, okay? And so my moles, which is 2.331, and divide that by the volume. So now when I get the answer, this I can round off to 4 significant figures, okay? And so this last calculation is the easy one because it's moles over liters. This is the critical part, okay, over here, finding the mass of the solution. It's important to remember that when you have molality, you don't have solution, you only have solvent, okay? So you have to find the amount of solution, okay, in order to carry out the next calculation. And that's the important thing in almost all of these solution concentration calculations, that you have to really mind your units and see that you're getting this, the right quantity. So the key concepts over here is know all your units and then be able to convert one concentration into another. We'll do more examples in class and see if we have any more questions with that in class.